we are laser focused right now on getting through the certification process,
Yeah.
getting the production ramped up. As soon as that's done, which is coming very soon, we are going to publish the specification and begin very detailed talks with the other industry stakeholders to potentially publish this as a standard. And we will be in parallel to that supporting the commercial rollout of our systems.
Okay.
So
Yeah,
there's some first vertiports that are already in the works that are already being constructed today.
Right.
And we need to supply chargers to them.
Formerly the captain for an electric car racing team for the University of Waterloo, where he studied, who later co-founded a robotics company that made pitching robots for the Chicago Cubs, Robert Rowland is an engineer on the ground support equipment team at Joby Aviation, where they are developing an all-new charging system to address the unique challenges of high-tempo electric aircraft operations, creating the critical infrastructure needed to make widespread zero-emission air taxis a reality. Robert is also our guest today, and this is the Sky Zero podcast. We've got Robert Rowland with Joby talking to us about the GEACS charging system. So Robert, thank you so much for taking the time out. I really appreciate you taking the time to come speak to us today.
Yeah, of course. I'm excited to share more of what we've been working on.
Very cool.
Pretty secret up to now.
Right. You know, it's weirdly hard to get information about GEACS sometimes. Should I call it GEACS or GEA? I keep spelling it out. It sounds silly. What do you call it?
Most people internally seem to call it geeks for now.
No
but I
way.
think it's still up for debate. We don't have a hard idea on how that's to be said.
Okay, that's awesome. I'm calling it geeks now. That's just too cool. So yeah, let's start with you. I mean, let's talk about who you are and a little bit about your background.
Sure. Yeah. So I'm a mechanical engineer. I went to the University of Waterloo in Canada, which is a co-op program. Got to work for a bunch of cool companies over the course of that co-op program, including like Toyota, Babcock & Wilcox, Tesla, Apple, and then EV research lab where I got to see some like very early days R&D efforts that General Motors was doing in the electric vehicle space. And then I was also, during my schooling, part of the University of Waterloo Formula SAE team for the electric side. So we were designing and building an electric race car as students to compete in a student competition. And that's where I initially made a lot of connections in the EV world and really got my feet wet working on all aspects of designing and building electric vehicle systems, and kind of fell in love with that. When I graduated, I went and did some other things for a while. I designed pitching machines for Major League Baseball, and I went to work for Apple eventually, but then felt the pull back to the EV engineering world. And one of my close friends from the Waterloo Formula SAE team, Alex Bondarenko, heard me grumbling about being bored with other work and asked me to come back to Joby to work on charging.
Very cool.
That's when I came back in 2021.
Cool. So personally, I'm in Toronto, so I mean Waterloo means a lot to me. That's really neat. I'm aware that they had an SAE team. That's really cool. Did you guys win that year? Is this the big Australian race, or am I getting that wrong?
We have performed well recently, but not won.
Great, thank you. That's really cool. So to your point about getting connected, it was a fellow Waterloo alum that pulled you in. Okay, cool. What's it been like so far? How have you found it working there?
It's a super exciting company. When I joined in 2021, it was only 2 people working officially on the charging team at that time. There had been some different efforts across the company to build charging solutions for Joby's early aircraft, but they had always been more from the perspective of just get it done and explore different ways to charge the aircraft. And then starting in 2021, there was a concerted effort to actually make, what are we going to do long term? And that was the beginning of what became GEACS. Kind of before I joined, there had been a lot of research on different aircraft architectures, how eVTOLs might need to be designed to perform well in an air taxi environment. And they came to some of the conclusions that drove the decision to build GEACS.
Okay.
Just how,
tell me about that. I was going to get to it, but I imagine they looked at CCS and GBT and sort of all the others, or did they were maybe I've known definitely I've known teams that were pre-inclined to build versus bring in. But how did they sort of look at those and say, oh, it doesn't meet the spec? Or to your point, they were really looking at like what would an air taxi need, right? So what about that led them to build and yeah, like just start talking about GACS basically. Yeah.
Sure. Yeah. So, I mean, that's like something we definitely want to do always. If there's an off-the-shelf solution that meets our needs, of course we want to buy that. It's always cheaper usually to buy something than to make something. But when Joby's thinking about operating air taxis, we need to not think about like the cheapest solution just for charging or the best solution just for charging. We need to think about the whole picture.
Yep.
How are we going to operate air taxis in a way that is efficient for the whole system and safe for the whole system? And it turns out that when looking at the global optimization problem, it's worth it to trade some more complexity onto the charging system. And in some cases, move some of the cost of the overall system onto the charging system in order to yield some overall benefits. So by moving to a system like GACS versus CCS, we can charge faster, we can have a safer aircraft, and we can get that aircraft to have some additional capabilities that wouldn't otherwise be possible.
Yeah. So I'm sitting here biting my tongue because I've been looking at like there's this one PDF you can get on Twitter if you search for like GX geeks. It's this one thing that comes up and it shows you like what it looks like. And then at the Oshkosh Air Show recently, I actually got to hold the handle for the first time. And I'm like, okay, wow, this is great. Like the engineering on it. Oh, you've got one right there.
Yep.
Of course you do. Yeah. So, but for folks who are just tuning in and they have not spent as much time obsessed over this as I have, or not nearly as much as you have, right? Like, so walk us through, because it is pretty different, right? Like, if you think about like CCS versus CHAdeMO versus GBT, they're pretty similar. There's some communication pins and there's DC and there's AC, and that's kind of it. But with Geeks, it's pretty different. So walk us through what those differences are.
Yeah, so Geeks, I should say for a second, is really just a definition of the interface.
Right.
It is defining the boundary between the vehicle and the charging system. And right now there's only one implementation, Joby's implementation of GACS. But in the future, once we publish this as an open specification, hopefully being adopted into a standard, we think that there will be many other implementations of GACS with different ground systems and different ways of aircraft connecting and using the charging system. Mm-hmm. That standard consists of, or that interface definition consists of fluid ports, so we can pump fluid on and off the aircraft. In our case, it's 40% ethylene glycol with some corrosion inhibitors. And then we have two independent DC charging channels, so we can independently send like plus and minus, two separate independent channels to charge, in our case, two separate battery packs. Mm-hmm. And then we also have a data connection. Mm-hmm. So in the middle, it's kind of hard to see with the lighting, but we have a set of pogo pins that allow us to communicate between the aircraft and the charging system one way, and also have some interlock functionality between the aircraft and the charger, so they can both agree that they're in a safe state, and then the remaining pins are to provide auxiliary 48-volt power from the charging system to the aircraft.
Oh, okay. And you are 48-volt auxiliary, right? So I wanted to like deep dive in all of the places at once, and that's difficult to do in a conversation. So let's start with the liquid part, because to me that's like the part that usually blows people away. It's like, they're doing what? Like, I remember when I first got an EV, my neighbors were like, "Can you wash it?" I'm like, "Well, yes." I mean, of course. Can you charge it in the rain? Yeah, and of course, right? And when I explain, that's the thing about Geeks that makes it so different is, or to your point, that's just the interface. But that's what makes the Joby charging system so different, is that you are running coolant through it, and not just electricity. So let's start there. Walk our listeners through why, would you do it that way? I've got my guesses, but I want you to tell the story.
Sure. So specifically on the fluid side, if we take a step back for a second and think about like, how do we charge faster? what is the limiting factor at a physics level to charge a battery very, very fast. And usually at the end of the day, it's actually a thermal problem. Battery cells have this like complex matrix of variables or factors that affect the ability to charge and discharge the battery cell. And the most important one of those is temperature. If the cell gets too hot, then you risk going into thermal runaway. So you need to slow down the rate you are charging or discharging the cell to ensure you don't exceed that temperature limit. If the cell is too cold, then if you charge too fast, you risk lithium plating or other negative effects on the cell's electrodes that could limit the life of the battery pack. So when we are designing a charging curve, so the relationship between state of charge and the current we're going to push into the battery pack, we're constantly looking at, for that specific state of charge, what temperature ranges do we need to stay inside? So when you're dealing with large battery packs that are charged fast, you're almost always going to have some form of active thermal management system. In your automotive electric vehicle, like pretty much all EVs on the road that are built recently have some sort of liquid cooling system where they're pumping liquid through the battery pack to some form of heat exchanger, like think of a radiator in the front of the car, which air passes over it and cools that coolant down, and then it goes back to the battery pack. And it's not just about keeping the battery pack cold, but you also have to bring the battery up to temperature, so they'll also have a heating system in that loop. Those systems, you have to strike a balance between the amount of mass and the amount of volume you're going to take up on the car versus the amount of cooling capacity you have available. So in your average EV, oftentimes when you hook it up to a very high power DC fast charging system, they're going to charge at a high rate for a few minutes in some cases, and then they're going to slowly start tapering off the power, not because the charging system that you're connecting it to doesn't have the power available. It's because you're starting to overtemp the battery. The thermal exchange system on the vehicle wasn't designed to continuously reject the amount of heat that's being generated by the battery pack during charging. So when we sit down to design an aircraft, we have to think, okay, do we want to put a active thermal management system on board the aircraft, and how much continuous heat rejection capacity do we want to design into that thermal management system, governing how quickly we can charge? And in an aircraft, the mass is very, very important, like far more so than an automotive application. We want to shave out every possible gram that we can out of the system, especially for dead weight. So a cooling system is considered considered dead weight to us because it's not energy to extend the flight, and it's not generating power, and it's not structural necessarily. It's not like supporting the airframe. So that mass, every additional unit of mass that we add in dead mass means that we have to add mass elsewhere in the aircraft to support it.
Right. So if that liquid cooling loop, took up, 100 pounds, probably not that much, but let's say, and you could take it out, then that's 100 pounds more people you can carry. And of course, there's these famous equations around weight and aviation where it can actually be even better than that sometimes. I'm probably getting it wrong, but basically you can size everything else smaller, the smaller you get. So yeah, that's what I wondered, right? Is that we're able to take it out. And to your point, like if I charge my EV on a hot summer day, and then I'm driving down the highway after, and I still have the AC on afterward, like the heat pump is running like mad. And I think it's because like I just like supercharged, the Ioniq 5 charges at like 230 kilowatt or something. And so it's using the same cooling system to cool down the battery and us. And I've never heard the heat pump go so loud as when I've just been charging. But does this mean you get to take like all active cooling off board? I mean, I guess if you're operating at like 4,000 feet, like it's cooler than when you're sitting on the asphalt in Phoenix in the summertime. But like, how much cooling are you able to take off board? Do you still have some on board or not?
So in the Joby aircraft, we actually have no active thermal management systems on board the aircraft for the battery packs in flight. So not thermal management systems that are rejecting heat to the outside environment. We do leave coolant on board, but that's not for the purpose of rejecting heat. We do have a thermal management system on board the aircraft, but it's for the cabin.
Wow.
air conditioning system to cool the cabin. And that is also something that is enabled by GEACS. So, as I said earlier, batteries are very dependent on being within an optimal temperature range for their state of charge, not only for the charging process, but for the discharging process. So with GEACS, if we keep it connected right before the aircraft takes off, we can bring the battery packs to an optimal temperature for takeoff. And then in an air taxi environment, you're usually doing short flights.
Oh, right.
We can identify what the next flight is going to be and bring the battery packs to a temperature before that next flight that is going to be able to see them through to the landing.
Right, right. You've got a decent thermal mass. It's going to take time for its temperature to have changed too much. And short times, we're not talking about 8 hours across the Atlantic here. Okay.
Yep.
Neat. So that's
Yep.
considerable weight savings then. You're able to find a lot of dead weight there. That's neat.
Massive weight savings. And we're also able to have a much bigger, more powerful cooling and heating system in an off-board system where we don't care about mass, we don't care about volume.
Right.
We can go buy a chiller off the shelf pretty much and stick it 100 feet away from the vertiport
Giant
with a set of
industrial
lines
strength
going
chiller,
to our dispenser.
No problem. Yeah.
And
you don't have to carry
we
it.
can have far more cooling capacity on the ground to be able to exert a high degree of control over the temperatures of the battery pack throughout the charging process. So we can keep the battery packs in that optimal temperature range throughout pretty much the entire charging sequence.
Amazing, amazing. What can you say about what this does for your charging curve?
I can't share any specific numbers for like the currents and voltages that we're running with, but I can say that GEACS can support up to 1,000 volts and 300 amps continuous.
Wow. Okay. Okay, but also I'm thinking about sort of shape. And to your point, can't talk speeds and feeds, and I get that. But if I think about, like, I mentioned my Ioniq 5, I'll be an automotive nerd for a minute. It sort of goes like high, and then it stays high for a little bit, and then it doesn't come down that much, but then it sort of flattens out. And then sort of around 60, 70, it starts to really kind of slow down, right? Other cars, will sort of like the Tesla famously is like goes really high and then sort of comes down really fast, and they're almost like encouraging you to gas and go quick and don't sit there forever. But then other cars, they sort of get to 70 and just sit there the whole time, and that's in part because of limitations they've got. When I think about your charging curve, am I going to imagine like one of these mountains that goes high and stays like a table, or is this more like a high curve that then flushes down, or can you talk about the shape of the curve?
Yeah, so due to our ability to control the temperatures of the battery packs, we can stay at high currents for longer.
Right.
Which is the big part of why GEACS enables faster charging. It's not because we're going to higher absolute powers. It's because we're able to stay at high powers for longer.
Right. Got it. Which usually ends up winning in the end, instead of a super big number at the beginning and then slowing it down. Okay, yep. Awesome, cool, thank you. To your point, 2 DC channels. If I remember right, on the S4, the charging port is under the wing. So I think I just assumed that there would be one on each wing. But if there's 2 DC channels in the one port, is that right? Is there sort of just one for the entire aircraft, or how does that work?
There's 2 charge ports per aircraft.
Got it.
So
okay.
Each Joby aircraft, at least in this first version that we're launching, has one charge port on the left and one charge port on the right. And when that aircraft comes into land, we plug 2 identical GEACS charge handles in.
So each wing has 2 batteries. So you're talking a total of 4.
Correct.
Got it. Okay, cool. Which, again, is better for redundancy and everything else. And if I remember right, charging speed, too, I guess. Although, if you're putting all of that into one big cable, but it still seems like it would help with charging speed. Is that right?
Yeah, if you were to combine it into one handle, you could do that. If we were to have 4 of the same size channels as we're putting in our 2-channel system in one cable, you could do it. The limitation might just be the mass of the cable. These cables are already getting quite heavy.
Yep.
But that's not the reason why we did what we did. There's other reasons to keep the charge ports separated on the aircraft, both for keeping the systems isolated and not having mass passing over the center of the wing. Hopefully one day someone from the charging team can come on and tell that story.
Got it.
Sorry, cool. From the aircraft team.
So we covered the liquid cooling system. We covered DC inputs. Were there other types of things about CCS that you wanted to improve on?
Yes. So when we began developing Geeks, we were initially focused primarily on safety, and we still are. Safety is our number one priority. And then we also wanted to get to faster charging. And in looking through what was required to enable our standards for safety and charging speed, we started to see some desires in cybersecurity, our ability to pull data off the aircraft, and where we were doing the computation for optimal charging that necessitated a better data and communication pipeline than existing charging standards such as CCS could enable. CCS has the option to use power line communication to transfer data from the vehicle to the charging station, but it's limited to about 1 megabit per second. And our math indicated that we wanted to go far beyond that, multiple orders of magnitude more data bandwidth. So what developing an all-new standard unlocks with GACS is that we could add a new means of transferring data between the vehicle and the charging station. We added a 2.5 gigabit per second T1 Ethernet connection in the charge handle connection, in the charge interface, that allows the aircraft to stream data down to the charging station in a secure fashion. The data stream is limited in hardware to be one way, so there's no cybersecurity risk in that interface.
Nice. Okay.
But the aircraft can stream vast quantities of data about its current state through the charging process, as well as just general purpose data. Let's say if we want to transfer data from the previous flights, records of the previous flights, down to the charging equipment, we can do that. And that enables us to one, have a faster charging speed, which I'll talk about in a second, but we can have data available on the ground support equipment that's been securely pulled off the aircraft that can be used to analyze the current state of the aircraft for predictive maintenance, for example. So we can see is some component on board the aircraft trending in a bad direction. We can then preemptively or proactively schedule maintenance work that we otherwise wouldn't have been able to know that we needed to do.
Got it.
On the charging side, with existing charging standards, the decisions around the charging process are primarily made on the vehicle side. So the vehicle looks at all of its all of the sensor data that's coming in from its batteries, its records of what the batteries have been up to over the period previous to the charge, and it decides this is the voltage and current that I want to be charged at, and it sends a current limit to the charging station. And then the charging station basically just tries to do its best to get up to that current request. We wanted to go beyond that. When you're running an air taxi operation, you have the opportunity to forecast what is the next mission this aircraft is going to be doing. What is the current state of the power infrastructure at the building where the vertiport is situated? What is the current state, in our case, of the cooling system?
Right.
And knowing all that information allows you to maybe make a different decision than you would if you only had the information that the vehicle has on hand. So by streaming a large amount of data from the aircraft, in this case like raw battery temperature data, individual cell voltages, pressures of various points in the fluid system, we're able to have a higher, more complex level of charging optimization by transferring all that to the aircraft, running computations on board the ground support equipment with more computational power to make a decision for the optimal charging profile.
So there's another weight savings there. We can now have more computation because it's part of the charging system, or is there more to it?
Yeah, so it could potentially be a weight savings. You could have more complex computing hardware on the ground. It's also a benefit from a continuous development perspective. So anything on board the aircraft, in the sake of safety, we want to have anything that goes on board the aircraft, any change to the software or hardware on board the aircraft has to go through a very, very rigorous review and testing process. But for charging, we might want to continuously update the optimal charging sequence for a given aircraft. Maybe every week we want to be continuously pushing small little tweaks and updates to optimize that process, which if we were to put those algorithm optimizations onto the aircraft side, we would be very like delayed in our development process.
Right.
But by having it on the ground support equipment, we are freed to be continuously updating at a much faster way. We still go through a rigorous review process, but it's not quite to the same levels as is necessary for an aircraft that you're trusting with your life.
So when I think about Tesla doing over-the-air updates, maybe you can do that with the S4, but to your point, it would still have to go through like a full certification round. And so now, by being able to make this software changes to the ground support equipment instead, it allows a fast. Wow! So you're really speaking my language on the continuous delivery side. That's a very software thing to do, and thinking about how can we continuously get the software updated. Okay, cool. Cool. Okay. So I guess the 1 megabit per second that CCS did have, I can see that being is maybe enough if all you're doing is saying, this is how many amps I want right now. This is how many amps I want right now, over and over and over again. But to your point, you're doing a lot more with it. Okay. Neat.
For us, it's very, very critical that the ground support equipment is not able to modify the aircraft in any way that is not immediately and reliably detectable by the aircraft.
Right.
That's what drives this.
Got it. Cool. So famously, you guys have flown in Dubai now. With some digging, I found that you guys did some serious flying in Korea, right? And almost like a championship kind of competition kind of situation. And of course, there in Marina, KOAR, I think, is where you normally do your flying. So at least those 3 locations, right? And there's a fair amount of difference between those 3. So when you think about what it takes to charge and how the situation changes it, like, what can you say there? I mean, have you learned anything taking it to different situations, for instance?
Yeah, absolutely. Yeah, and we're also currently flying in Osaka, Japan, every day.
That's right.
And we flew at the Salinas Air Show out of our.
How did I forget Osaka? That's the one that's happening now.
And there's a host of others. So when we developed our actual charging systems to support aircraft flight testing and continue supporting the aircraft, we took kind of a phased approach where we started off by building a very agile, lightweight charging system out of a series of power supplies connected directly up to mock-up charge cables. And then after that, we took that solution, we learned from it, then we built a next-generation charging system that allowed us to pack all of the functional bits required to build a GEACS compliant charging system into a 20-foot shipping container. We built a number of those systems and we've deployed them around the world. So every time you see the Joby aircraft fly in Osaka or in Dubai, or for those Korea demo flights that you were discussing, or at our flight test facility in Marina, that's all using that 20-foot shipping containerized solution. And that's exactly the same functional system as we plan to launch commercially at our first vertiports. But now we are on the next phase where we're taking that system, we are miniaturizing it, we're packing it down into a system that can be integrated into real commercial sites, which have different kind of layout requirements and different spacing requirements. And we are currently now done the design phase for that program, and we are in the process of ramping up the manufacturing and going through the certification of it within NRTL.
Oh, that's exciting. Okay, cool.
So you should see some news about that system soon.
When you say certification, my brain leaps in 2 directions at once. And one is sort of like, UL, or in Europe there's a similar one, EC, I think. But you could mean FAA and EASA. Like, what sort of certifications end up being required?
So as this is a piece of ground equipment, we are able to certify it with a nationally recognized test lab in the American case. Those test labs usually offer multi-market certification options where we can work with one recognized test lab to certify the product in a variety of markets at once. So we're working with a test lab like that. This process is the same as the process we would use to certify any other automotive charger or even your washing machine or toaster in your house. UL is one example of a nationally recognized test lab, but there's others.
Got it. Yeah, fair. So, okay, but we don't need to go the FAA route. They're not looking into this.
No, we work hand in hand with the FAA.
Right.
They are aware of what we're doing, but the aircraft is capable of ensuring its safety before the next flight. The aircraft is always monitoring the condition of the charging process and the condition of its batteries, and it's able to stop the situation at any time automatically if anything was to go wrong. And that's really what the FAA cares about, is the safety of the aircraft.
Right. It's more the aircraft itself and not the ground equipment is sort of what I was getting at. Okay, cool. So charging system architecture, you've avoided numbers, and I get that. In automotive, we think of it as, there's sort of 400 volt and 800 volt. But also it's not just the number, is it? Right. It's sort of like the battery pack is maybe at one voltage, but then inverter systems might be at others and motors might be at others. Like how have you thought about the architecture? Like what can you talk about in terms of like how are all the components matched up? Or I think it's the Hummer EV that I'm thinking of. That's literally like it's two 400 volt packs, so it's really a 400 volt system, but it's kind of an 800 volt battery. And so they could do the 800 volt charging or something. I'm sure I'm getting all this wrong.
Sure.
But
so the GACS standard is a 1,000 volt charging solution. So, and those, the implementations of that system that we are building and installing can support the full range of the implementation. So we can support up to 1,000 volts independently across all 4 channels. Joby's aircraft uses a range of that, a little bit below the 1,000 volts, and each battery pack that we're charging stays completely isolated and independent of the other battery packs.
Right. So to your point, whatever that number is, it's not divided by 4, it's times 4.
It's times 4. So when I said we can do 300 amps, it's 300 amps times 4.
Wow.
Times 1,000 volts to get your power.
Right. Okay, holy cow. That's pretty insane. Yeah, that is definitely pretty insane. Is that megawatt level then?
So it can theoretically support up to 1.2 megawatts.
Wow.
For a single station install.
Got it. So you're giving Charn a run for its money in a way. Or what if... Do you... Okay, that sort of gets into another direction that I want to go with this. You said earlier, we want to... I don't know if open source is my words or yours, but release it, right, and make it a public standard, a public specification. If I understood you right, how would you see that working? Like, would you? I mean, just to pick 2 other large North American OEMs out of a hat, like if Archer and Beta were to suddenly, or if EHang were going to suddenly start looking at this, or Hart Aerospace were going to suddenly start looking at this, like how. What's the ambition inside of Joby for that? It seems like it would be good in a general way if that standard were out there, I guess. Mm-hmm. But yeah, like how do you guys see it, and what's the ambition for it? And talk about that part.
So our ambition is to publish this GACS specification as a standard, eventually, that can be adopted by anybody who wants to adopt it. That includes other charging equipment manufacturers and other aircraft OEMs, such as the ones you mentioned. We haven't gotten there yet because we want to stay laser focused on focusing Joby's own needs, so being able to support Joby aircraft flying every day, and also make sure that we retain the flexibility to modify our system as we're going through the certification process. There might be some like last minute tweaks as we work with the test labs to get our system through to being a certified product that we can deploy. Once we get through that process, we fully intend to publish a full set of documents of the entire interface specification that can be used by other people looking to manufacture their own solutions. But in the meantime, our door is open today, and we have a email alias that anyone can contact. It's groundsupportequipment@jobyaviation.com. It was on the bottom of that PDF that you're referencing. Yep. If there is an aircraft OEM or a charging equipment manufacturer that wants to reach out to us and start working with us today to adopt GACS or to suggest alternative design choices, we are open to that. And in fact, we already have had a number of different aircraft OEMs and other people in the industry, other stakeholders, reach out to us express interest and provide alternative suggestions, some of which we have implemented.
Yep. I don't know if you got a chance to read it, but I had published, I think you might have, an article about charging, right, and aviation versus automotive. And I sort of wrestled with it, you know. It's like, so I can totally see the allure of something like CCS. You could charge the F-150 Lightning that's airside, that's, you know, getting crew around at the airport on an apron, or anything else that you've got, which is a ground vehicle. I mean, that's a benefit to something like CCS. But at the same time, like, the combined in CCS means combined AC and DC, and nobody's doing AC charging in aviation right now. They're all doing DC charging. I assume that's for the same reason as what you talked about earlier, which is that AC equipment on board is extra weight that you don't need to have. So, like, CCS's one party trick, in a way, is that it does both, and you don't need that. In fact, it seems like it could be extra, if not weight, at least volume. I mean, these are not small plugs. And like the one that you were showing is also not small, but you're getting a lot more out of the footprint. You're getting cooling and data and 2 separate DC loops. Whereas with CCS, you're getting 1 DC loop, and you're not getting any of those other things. So I can totally see what would have pushed you guys that way. I think it was Josh Portlock out of Australia for Electro, the one that doesn't make an airplane, the one that makes chargers, was talking about how the thing about CCS that's kind of not great, when you're plugging it in horizontally, it works pretty well. Like, that's how cars go. But when you want to plug it into a wing, it doesn't. And it's not that it doesn't have locks, it does, but that those locks generally weren't implemented with this orientation in mind. And so they're more likely to fall out and be dangerous and cause shorts and things like that. So, yeah, all of this to say, like, I can see why you guys went the way you did. Have you ever had a heartache about that? Like, thinking, like, does it make sense for ground vehicles to also use geeks as a potential down the road in order to get some of that value that CCS brings? I mean, it couldn't have been an easy conversation, I guess, is where I'm going. Yeah, I mean, if you want to talk about that at all.
Yeah, certainly. So we don't take the decision to develop a new solution lightly. Like, the proliferation of new standards is not something anybody wants. Like, we would like to consolidate to one solution.
Yeah.
I think that there are other industries that would probably benefit from adopting GACS eventually, especially once we've done all the work to develop it and it's out there and available.
Electric
it might make sense to adopt it.
Yeah.
But what really drives it, and the main use case to make a new solution, is just air taxis. The mission is just so demanding and unique that if you want to operate eVTOLs in an air taxi environment efficiently, we see something like GACS as really the only solution. You can't have just a CCS connector and efficiently operate air taxis, because you're just going to be spending too much time on the ground, or you're going to have too heavy of an aircraft.
Yeah. I mean, the cooling, being able to operate your cooling, certainly to me, that's like, okay, I get it. You know, it's worth it at that point. And being able to combine 2 and 1 isn't bad either. So, yeah. So could we imagine an airside, maybe I should stop trying to make it so that airside ground vehicles can use it too. I don't know. I mean, is that crazy to think that airside ground vehicles, maybe they don't have the same challenges, but I guess I'm trying to save a buck for small airports that don't want to have multiple charging systems out there, I guess.
So they could adopt it, yeah. And
yeah,
GACS is quite flexible because of the way the communication protocol works, to do a range of different things using the same interface. So you can plug in in a vehicle that, let's say, only has 1 battery pack, and you can just tell the charger that, hey, your 2 charging channels are now paralleled. We've connected them to a single bus bar on board the vehicle, and we want you to charge in unison, and the dispenser will happily do that.
Got it.
Same deal if you were dealing with a vehicle that doesn't have cooling, let's say, or has a different cooling temperature range. You can command the ground charger to not use the cooling, or to follow a particular temperature profile that's needed by that vehicle. I haven't seen any driving forces for that yet, but it's not to say that it's not possible and that it might not be done in the future.
I mean, it seems a little bit silly. I mean, could I actually imagine like an S4 taking off and then somebody pulling up an F-150 Lightning? I mean, it seems like probably no. Like you maybe having another one land shortly after, but I don't know. So thank you for humoring me on that one. I appreciate it.
The other consideration is that these chargers are installed airside. And at FOBs, there's a high degree of control between airside and general public. So it's not like the general public would ever be able to pull up to these.
For sure.
And most of the vertiport sites that we're going to be operating at are also kind of separate elevated structures in urban environments or in other areas where you don't necessarily need to have ground equipment around.
Right. Yeah, I've got to start thinking vertiport and not airport. You know, I mean, airports have baggage handling trucks and all sorts of stuff running around, but a vertiport may or may not yet. They may be smaller, and choosing sites that are tight might be something you want to do. Okay, fine, I get it. So you definitely need that mini system, to your point. Yeah. What can you say about the miniaturized version?
When I say miniaturized, we're miniaturizing the dispenser. So that's the piece of equipment that gatekeeps the flow of liquids, coolant, and the data and the electricity on and off the aircraft. We're taking that piece of equipment and making it as small as possible, such that we can fit it into creative locations on these very constrained vertiports. So vertiports have some restrictions on clearance zones. So you need to have a big circle around the landing pad that needs to be kept completely clear on the surface of the landing pad. And then also there's restrictions about where you can place things even outside that zone with like a cone that expands out from the landing pad. So we want to be able to either put them low to the ground to the side of that landing pad, or in some cases even under the landing pad and pop up through the surface of the landing deck.
Got it. Okay, got it. So instead of like a 20-foot, TEU container, that we're talking about something that it almost sounds like it might be distributed too into sort of multiple modular components. Like part of it's under the pad, or.
Yep. So we're taking a modular approach where there is a dispenser, which the actual charge cable pops up out of, that has to be at the landing site or wherever the aircraft taxis into for charging. And in that dispenser, there's a core module which houses all of the functional bits to do with the charging process. And then we package that core module into different configurations to be reused at many different sites. So we're going to have a mobile solution that's on wheels and you can drag it around. And we've also got a solution that goes under the ground such that you can have a completely flat landing deck. And then when you need the chargers, it pops up out of the ground and you can connect it to the aircraft very quickly and efficiently. And then the dispenser, I think I said, is just the gatekeeper. It's connected to AC to DC power conversion equipment, which, thanks to the automotive market, is largely commoditized. We can buy AC to DC power conversion modules from various markets around the world for very, very competitive prices. And then on the fluid side, we're connected to a large coolant reservoir, so an insulated tank of coolant, which is then connected to a chiller. The tank serves as like a capacitor for the coolant, so when we first connect to the aircraft, we have this big reserve of very cold coolant to pump into the aircraft without having to size the chiller necessarily for the peak thermal exchange rates.
Okay, cool. So componentized, modularized, and also sort of, okay. So it sounds like certain things like that coolant tank could almost be sized up or down based on use case, need, available space. But to your point, this does also allow you to sort of go with sort of commodity equipment, like you're saying, the AC/DC equipment from the charging side. Okay, cool. That definitely makes more sense. I mean, for now, having it in a shippable container makes a lot of sense. And I think in certain circumstances, disaster relief in terms of like, were there a natural disaster? Yeah, I mean, a shipping container is, again, exactly what you would want. Of course, that's a disaster that's going to have a very large electrical connection still. But still, I could imagine it being dropped into place in a lot of different places and used. But yeah, in a vertiport, that's a big, chunky, cubular thing, which is kind of in the way. So yeah. All right, cool. Thank you. Can you talk about partnerships at all? Like when you think about current collaborations, strategic relationships in the charging ecosystem, anything you can speak to there?
Unfortunately, no, I can't share specific details beyond what's been already publicly announced. But you can see from our other public announcements, we've got pretty strong relationships with Toyota,
Yep.
Delta, Uber, ANA, and a bunch of others.
Yep.
Toyota especially, they've been very, very supportive of us. I run into members of the Toyota team every day at our San Carlos site.
Nice. Okay. Yep.
And there's also multiple ways to book a Joby flight through those partners. So you've probably seen our relationship with Uber that may enable us to book a Joby flight through an Uber and do multimodal transit. Let's say with a car share on the start of the ride that is synchronized with your ability to take a Joby flight and then have a car waiting for you on the other side.
Yep. The story where you guys sort of started out of Uber Elevate is such a neat tie-in, right? I mean, you can totally imagine you guys having Uber at launch and just having it work, where you can't necessarily imagine that with anybody else. But I think that's a part of my question for you guys around charging too. We don't know how this is going to go in aviation. There's not a lot of aviation charging networks yet. There kind of is. Aerovolt in UK, which is very general aviation, trainer oriented, the little GBT pipistrels. eGrid in Switzerland, very similar. There's a new one, Energy to Fly, out of the Netherlands that I'm talking to right now, and they're doing exciting things too, GBT and CCS2, if I understand it. Beta, of course, right, with the 40, 50 stations across the northeastern U.S. and even the southern U.S. and one in California, if I remember right. But so I can imagine all sorts of companies buying a Beta aircraft and needing a place to stop and charge it. And I can imagine them either throwing a mini cube in the back and using the GPU, ground power unit, or plugging into a Beta charger. With you guys, it's a little bit different. I don't really want to get too much into business model, but it probably impacts some of your decision making. Could I ever? What would the need be for a Joby Geeks charging network? Would you imagine that? Or I almost imagine you guys doing it a little bit more like an Apple style of no, we take care of it all for you. You don't have to think about where it charges. But maybe I'm wrong. I don't know how I got to that assumption, right? What can you say about how you envision the charging that you're working on getting out there in the world?
Yeah, so it depends on the path to commercialization for the market that you're talking about. This is not my area of expertise.
Right.
We've laid out 3 paths for commercialization in the quarterly earnings calls. So one of them is a Joby owned and operated air taxi service that you alluded to, in which we would control the full stack. We may also do direct sales of our aircraft. And then there's partner operations, like what we're working on with ANA.
Right.
And then,
or Delta, maybe. Okay.
Yeah. So in each of those types of markets, there would be a different solution to deploy the chargers, which is my job. My job is to build GACS, certify GACS solutions, and then we want to have that optimal charging system available to be deployed to those markets very quickly. So we are, like I said, building it to be super modular so we can deploy it really, really fast. And we've got all sorts of different options for how it can be put out. So we have a solution for every type of vertiport or landing site. And then we are also ramping up the production capacity to exceed the rate at which we're building aircraft. So you're never going to be bottlenecked by your ability to get a charger.
Right. It does seem like that needs to be kept up, right? I mean, if there's no way to energize these batteries, they're not going anywhere. So getting a proliferation of the equipment out there seems like it would be a big job. Okay, but to your point, I wish I was the kind of person that read earnings calls. I should have done that as part of my strategy here. But to your point, it could be either a Joby owned and operated, but there's also, we could sell the equipment, and there's also operating with partners. Okay, so you could imagine, based on that, a GEACS sort of charging network out there. Then, whether it's Joby branded or not, I mean, there'd be all sorts of models for that. Okay, but we might actually get hands-on with this as a aviation industry. It won't all be under wraps. Okay, cool.
Yeah, it won't be under wraps. There's definitely going to be units that are able to be owned by other entities. And if other entities want to start thinking about how to install a GACS solution, there's things they can start getting ready for today. So that's making sure you have a large grid feed available. You can start working on the space claim to install a system. And there's some other little details. We're probably going to start publishing some of those standards eventually soon, or advisements. But if anyone who's listening to this, wants to reach out to us about how can I install a GACL solution, just send us an email. We're happy to send you over some documents.
Okay. I imagine it wouldn't be too different than an automotive charging site. I mean, obviously higher electrical supply, and siting, obviously. Hopefully it's sited near somewhere where these things can land. So, I mean, that's big picture. But otherwise, like, I don't know, any other requirements that would be impactful?
The only big difference from an automotive charger is just the layout of the dispensers on the landing pad.
Got it. Got it.
There's a range of options there. You can go and just place it at the edge, at the disadvantage of having to land and then taxi over.
Right.
If you want to be more optimal, we have some other solutions that we can share to those that reach out to us.
Okay.
Hopefully we'll be able to be public about that soon.
Okay. Cool. Thank you. Appreciate that. What can you say anything about the future? Like, where's the standard going next? What's up next for you?
So we are laser focused right now on getting through the certification process.
Yeah.
Getting the production ramped up. As soon as that's done, which is coming very soon, we are going to publish the specification and begin very detailed talks with the other industry stakeholders to potentially publish this as a standard. And we will be, in parallel to that, supporting the commercial rollout of our systems.
Okay.
So there's some first vertiports that are already in the works that are already being constructed today.
Right.
And we need to supply chargers to them.
Yeah, for sure. Yeah, big job. Kind of switching from design, build to manufacture, scale, ship, deliver, implement, install. Biggest challenges so far, and anything, design, build, implementation, anywhere you want to go.
I would say that we were able to get to the 90% solution quite quickly, and then it's the next 90% which really bogs you down. There's lots of little details involved in making a complex system like this. I can't say there's any one big, massive technical challenge that has blocked us. It's a collection of little things that you would not expect really being the bane of our existence as an engineering team. But there's no real big blockers. If I had to ask Santa for some solutions to some of our problems, would basically be more thermally conductive, flexible materials. That would be a great one.
A moment you're most proud of?
I think once we completed the containerized system and really being able to stand back and look at it and say, this thing fully works, and watching it charge the aircraft for the first time, that's always a happy moment. Seeing your baby actually do its job for the first time.
Yeah. Cool. Where can you talk about where that was?
In Marina, California.
Yeah. Okay. Cool. I wondered if it was we had to do this for the Korea thing, or yeah. Okay. Makes sense. You would do it at home first.
Yep. Try to do everything at home first.
Yep. Obviously. What about and maybe this is almost more career long and not necessarily just where you are now, but anything that you thought you were right about, or anything where you've had to change your thinking, right, and learned something and realized oh no, that's actually not how this works. Anything like that come up for you?
Sure. Yeah, it happens all the time. I can't think of anything that would make a great story for a podcast, but there's been lots of cases where we spent a lot of time designing one solution, one set of geometry, then a year later we realize that it has a critical gap, or we missed one measurement and have to go back and totally redesign it.
I can relate to that. I mean, in software engineering, you're obviously it's a different story, but you're often pursuing a design and nope, that didn't work. I'm going in this direction now. Okay. So what is your favorite aircraft?
SR-71.
Yeah. Because of the speed, because of the engineering, tell me the story.
I just finished reading Ben Rich's book, Skunkworks, and I'm getting into Kelly Johnson's book, More Than My Share of It All. and
Yep.
I really admire like how those teams operate. It's something that like we as Joby look to is like how did the people before us develop these aircraft so fast with such like a high rate of success, and we try to learn from that. And like they were a very admirable team.
Cool. I've heard a couple of stories out of that one, but I haven't actually read it yet, so I will go away and do it. So you recommend?
Highly recommend you should read it. Yeah.
All right, cool. Favorite airport?
SFO is pretty good.
Yeah?
Yeah.
How come?
It's fast, efficient. They've got the
Yeah.
new scanners.
I like that it has a BART station,
Yep.
but I'm just being a public
good too.
transit nerd, I suppose. Yeah, no, it's a pretty good airport. All right. Any shout-outs? Anything that you want to call out? Anything that's giving you joy right now, or anything you want to shout out?
I will say one thing for anybody listening to this that wants to get ready for vertiports. We have people that own real estate, people that really want to get to their work faster. They want a shorter commute. How can they get ready for building a vertiport? And the number one thing is to start upgrading your grid connections now.
Yeah.
If you are working on an airport renovation project and you are looking to upgrade your transformers for more air conditioning, take the time to put in the headroom for aircraft chargers. Ideally, we want up to 500 kVA per
Yep.
charging station. We can work with less, but that much is ideal. Please, please, please start doing
Yep.
it now.
Yep. Yep. These are not always fast permits to get, nor fast connections to bring in. Okay. No, good. That's a great call out. Cool. So, Robert, thank you so much for being on the show today. We really appreciate you. This is a great conversation.
Yeah, thank you. Thanks for giving us the opportunity to tell our story.